Hey, welcome back to your favorite pre-calculus class. We're going to look at functions and their graphs, specifically visually. So if you notice the graph there in red, let's find the domain of that, or the set of all x values. So if I'm reading this, I'm thinking to myself, well, it's going from this x value, not including that -2, right? Notice it's open, up until, and all of this is defined in between, up until that 2 right there, right? So I'm reading the graph from left to right. So my domain is from -2 to 2. I do not include either of those, so we've got the open parenthesis on those. If you want to do the domain with set notation, it would be I'm less than 2, I'm greater than -2 in set notation, right? The set of x such that x is less than 2 and greater than -2. Now let's go ahead and do the range. So the range, I'm looking vertically. I'm like, hey, what's my lowest y value here? It looks like it's -1. Both hits it, both spots there, but we don't hit it, right? It's open. It's open. So I'm not including -1, but it's hitting all these y values in red up until its highest y value there is 1. It looks like it does hit that y value of 1. So again, I'm looking from low to high. From -1, not including that is open. That's an open y value up until a +1. It does hit that +1. If you want to do it in set notation, this is set of all y's. Let's say I'm less than or equal to 1, but I'm greater than -1. Now let's take a look at our intercepts on this, our x and y intercepts, right? Now remember, anytime I have an x-intercept, my y value is 0. Anytime I have a y-intercept, my x value is 0, right? So where do we cross the x-axis? Where does it intercept the x-axis? Where do I have y values of 0? Right there, 1, 0. And it looks like I hit over here also, -1, 0. So 1, 0, and -1, 0, those are both of my x-intercepts, 1, 0, and -1, 0. My y-intercept, where does it cross the y-axis, would be right here. Here's my y-axis. It looks like it hits right there at 0, 1. That's my y-intercept for this graph. Got a new graph here in blue. It says, first find the functional value. Can you read the function notation here? Remember, typically we have f of x, right? So this is saying find the functional value. Find the y value. Remember, f of x is a nickname for y. Find y when x is -2. That's what it's saying. When my input is -2, find the y value. Well, let's go to our input, our x value of -2. What's the y value? So I'm like, here's my -2 for x on the graph. I find the corresponding point right there, -2, 1. So f of -2 spits out that y value of 1, right? We have a y value of 1 on the graph when x is -2. Now this part B here is saying find all x values such that f of x, in other words y, is 3. When y is 3, let's go ahead and find a y value 3. So on the graph, here's a y value 3. Let's follow it over. There's no y values over here that's 3, but if I follow it over here, oh, there we go. That point has a y value of 3, right? And so what's the x value there? 5. So an x value of 5 satisfies f of x equals 3. In other words, f of 5 is 3. Right? That's what they're saying. When the x value is 5, it's spitting out a y value of 3. Third part of this, part C, is saying, is f of 3 positive? What is the functional value? What is the y value when x is 3? Let's find that first. When x is 3, well, here's an x value of 3. Let's find the corresponding point on the graph. It's right here. When x is 3, y is about -1 or so. I don't know, approximately, right? I don't know how exact that is. But f of 3 is about -1. So is it positive or negative? We do know it's below that x-axis. It is negative, right? That's all we're answering on that. is that negative. And now let's get to our domain. Let's practice our domain and range on this one. Let me erase this blue here so we can do our domain. So our domain, we're looking, well, what's the lowest x value? And it looks like everything is defined in between there. I don't lift my pencil when I draw this up until my highest x value. Well, my lowest x value is a -4. Notice it's filled in. So I'm going to put a bracket on that. And then my highest x value is a 6. It's also filled in. All right, so we're going to bracket that. Let's go ahead and do it with our set notation. X such that x is less than or equal to 6 and greater than or equal to -4. And that's our domain on this one. All right, now we're asked for the range, find our range. So what's our lowest y value? It looks like it's a -2. It is filled in, so I'm going to include that -2. And then it looks like it hits all, the graph does hit all these y values up until, looks like the highest one is up here at 3. So it goes from -2, including it, and then it does hit the 3. So -2, oops. So we're going from -2 up until that 3. Both were included. So go ahead and pause the video, make this a you try it problem, and then we'll go through the answers. Now, first one here, we're finding the y value, functional value when x is -1. It looks like it's right there. So f of -1 is that y value of 2. Where is the y equal to 0? Let's find where the y value is equal to 0. Looks like it's right here, here, and here. So when x is -2, 3, and 5. Now let's find the f is f of -3 halves, f of -3 halves. So f of -1.5 is about right here, right? That's between -1 and 2, and f of -1.5. So it's like a positive 1.3 or something like that, right? So it's definitely positive. F of -3 halves is about 1.3-ish or something. I don't know, but it's positive, right? That's all we care about. What's our domain on this? Well, it looks like our lowest x value is -3, but it's open, right? Notice that's open. Everything's defined up until 6, but it's closed. So -3 up until 6. -3 up until 6. If you want to put in set notation, it would be set notation like that. Part E is asking for the range. Our lowest y value here is -4. It's not defined. We're not going to include it, right? -4. But we do hit all these y values up until it looks like the highest y value is a 4 right there. It is filled in, right? It's not like it's an open hole or anything. So we're going to include that. So the -4 is an open at the bottom, not included, up until a +4 at the top. So you have y such that y is less than or equal to 4, greater than -4. And finally, the last part, what are your x and y intercepts? Well, the x-intercepts, we already denoted it. It hit here, -2, 3, and 5 is where it crossed. Those are all -2, -3, 0. Or no, I think that was a +3 and 5, 0. We have 2, 3, and we're crossing the y-axis right there, 0, 3. 0, 3. So again, our x-intercepts were -2, 3, and 5. Our y-intercept was 3. So there's some more information we can gather from graphs, and that's whether they're increasing as we go left to right or decreasing or constant, and if we have some minimums and maximums on those graphs. So technically speaking, a function is increasing. Let me draw you an increasing function. Like here's one that's increasing. Notice that if I pick an x1, that's less than x2, then f of xy, its y value will always be less than f of x2 if it's increasing. That's technically what's going on when you're increasing. So you're going up and to the right. So it's kind of like you're going uphill, right? You're decreasing, right? This would be a function that's decreasing if you're going down and to the right. So in other words, if x1 is less than x2, f of x1 is greater than f of x2. Is the technical definition of decreasing. A function is constant if I pick an x1 less than x2, but notice the f of x1 is equal to the f of x2, right? It's just flat, constant. That's a constant graph. The graph is horizontal. Relative maximums when you have like a peak. So like that would be a max right there, relative max. You could have a relative min as well. And we'll talk about absolute mins and maxes later in the course. Let's go ahead and read this first graph here. Where is this function increasing? So if I'm going left to right, where is this thing increasing? When you want to name this in terms of the x value. So hopefully you can see that we're increasing here, right, on that section, which is from -3 to an x value of 0 on that. That's where we're increasing. So I'm increasing from an x value -3 up until 0. And then notice I also have another spot over here where I'm increasing. I'm going up and to the right over there as well. So not only here in black, but also over here in black. That's from an x value of 2 to an x value of 4. From an x value of 2 to an x value of 4. Now, where are we decreasing on this graph? Right here, we're going down and to the right. So it's from an x value of 0 to an x value of 2. We are decreasing on this graph. And we leave these, whenever we're talking about increasing, decreasing, we always leave these as open intervals. And I'll address that in the next graph as to why on that. Now, do we have a top of a hill or a highest point in an interval, a relative maximum here? You know, where do we have a relative maximum? Hopefully you say right here is a highest point in an interval, right? Top of the hill there, so 0, 3. So we have a relative max of 3. It occurs at x equaling 0. So the relative max location, if you're gonna name it as a point, is the point 0, 3. All right, this is a relative max up there. Part D, what is the relative max? Relative max, that's the y value, is 3. It is 3. Again, it occurred at 0, right? X being 0. What's the relative minimum? What's our relative minimum? Hopefully you can see on this graph that you have this point here. It's not on an endpoint here. You've got a lowest point there. We've got a relative minimum here, which is 0. What is the relative minimum? Relative minimum is the lowest y value is 0. It occurs at x being, that was an x value of 2, I believe, 2. Or at the point 2, 0. So x and y. All right, let's take a look where we are increasing. So go up and to the right. So if you notice I'm increasing from here to here. I'm increasing. That happens from an x value of -2 until an x value of 0. -2 to 0. And then hopefully you see that you're also increasing over here from an x value of 3, up until an x value of 5. Again, these are always open intervals. It's really, this is kind of a calculus discussion, but why do we only speak of increasing, decreasing, and so on with open intervals? Because at the end point, like let's take this end point at -2. If I take the slope of the tangent line, which is the rate of change at that exact moment, the instantaneous rate of change, the slope of that line, that red line, is 0. It's constant. It's not increasing, it's not decreasing. Right? It's constant right there. So that's why we just say, let's just forget about this and let's just go between them. Because we don't care about what it's doing. Or even right here, I mean, it's not even defined right there at the end point, right? Well, that's a whole nother issue, right? So I'm increasing up until 5, but it's not even defined there at 5, so I can't be increasing, decreasing, constant, nothing there, right? So again, we just leave it with open intervals for these intervals on which you're increasing, decreasing, constant. Okay. All right, let's do where are we decreasing now. So where am I going down and to the right? Well, hopefully you can see from an x value -3 to an x value of -2, -3 to -2, I'm decreasing. And I'm also decreasing over here. So I'm decreasing here and I'm decreasing there. That would be an x value of 0 until an x value of 3. 0 to 3. So from -3, -2, and then 0 to 3. Now we're going to list the numbers where we have a relative minimum. Relative, meaning in an area, do I have a bottom of a valley? Relative minimum. Well, hopefully you can see right here is like a bottom of a valley. If I forgot about the rest of the graph, hopefully you can see that's a lowest point right there in that area. Bottom of the valley. That's relative, meaning local. Local. Not on the entire graph. I just am looking for, do I have a bottom of a valley somewhere? Right? That's a relative minimum. So I have a relative minimum of, that's the y value, -3. Where does it occur? It occurs when the x value is -2. Okay, so that's that first one. Now let's do the other relative minimum right here in black. We also have a relative minimum, a bottom of a valley of -5. The relative minimum is -5. But it occurs, that's really what they're asking here, it occurs at that x value. So where did they occur? When the x value is -2 and when the x value is 3. What is the relative max? Well, let's go ahead and find the relative max. Do we have a top of a hill? Yes, right there in red. Hopefully you can see that's kind of a top of a hill. If I forgot about the rest of this graph, those areas in red that I just crossed out, hopefully you can see that that is the top of a little hill right there. In an area, I have a maximum in an area. That's a relative or local maximum. So I have a relative max of -2. It occurs at x being 0. So what is the relative max? -2. What were the relative minimums? We already named those over there. We have relative min of -3, and we have a relative min of -5. All right, let's move into our domain now. Our domain goes from -3, looks like it includes it, and then it includes all these x values in between up until 5. So do not include 5. So from -3 included up until 5. Or if you want to do it this way, it's another way to write that. Our range, let's do our range. Our lowest y value is a -5. It looks like it does hit there. Our highest y value, it does hit it over here. I know it doesn't hit it right there, but it does hit it over here. So y value of 0. So I go from -5 to 0, including both of those. All right, now we're going to get into symmetry. So if something is symmetrical with respect to the x-axis, symmetric with respect to the x-axis, then that means if I have a point up here, xy, if I flip it about the x-axis, I would have this symmetric point down there. Like, let's say that this point is, I don't know, 3, 2. Then I would also have on the graph 3, -2, if this graph is symmetric with respect to the x-axis. So let me give you an example of a large graph that's symmetric with respect to the x-axis. It would be like this. Every xy has an accompanying x -y. So that means you're symmetric with respect to the x-axis. And the way that you test that is you plug in, you replace y with -y, and you see if you get the same thing. Okay? So that's symmetric with respect to the x-axis. If you're symmetric with respect to the y-axis, that would be like the quadratic y equals x squared, right? If I have the point xy, like maybe that's 1, 2, then I would have the point -1, 2. This is symmetric with respect to the y-axis. See how it flips around the y-axis there, right? It's kind of like the y-axis is the fold in the paper, and you're flipping the paper over both sides, okay? Now, if you're symmetric with respect to the origin, that means that every xy that you have, you'll have, it flips it about both the y-axis and the x-axis. So it flips it down here. So this xy would be -x, -y. So it flips it about both axes. So I'm going to erase this so you can see that. So for example, if I have the point 2, 8, I would have -2, -8 on the same graph. I'm symmetric with respect to the origin. Symmetric with respect to the origin. Okay? So let's look at these graphs down below and let's see which one they are. This first one here, I say, well, if it was symmetric with respect to the x-axis, I would be able to see, oops. If it was symmetric with respect to x-axis, I'd be able to see that same point down there. It's not there. So it's not symmetric with respect to the x-axis. Is it symmetric with respect to the y-axis? Well, this point would be over here. If it was symmetric, it would also have that point over there if it's symmetric with respect to the y-axis, right? And finally, is it symmetric with respect to the origin? Well, if it's symmetric with respect to the origin, it flips it here and then here, so it would be down there. Symmetric with respect to the origin is symmetric about both axes. And it's not. So I just say, oh, there's no symmetry for this. It fails all three. Let's look at this next one. Actually, I'm going to skip this one for a minute. Let's look at this third one right here. This one, hopefully you can see, is symmetric with respect to the x-axis, because that point flips around and is right there every time, right? Flips. You see it's symmetric with respect to the x-axis. So this has x-axis symmetry. Let's go to this next one there, the second one. And let's start testing points. Is it symmetric with respect to the x-axis? Well, if I had the 1, -2, I should have the point 1, 2. So it's not symmetric with respect to the x-axis, right? Is it symmetric with respect to the y-axis? Well, If I had the point 1, negative 2, and I flipped it about the y-axis, I should have the point negative 1, negative 2. I do not. So it is not symmetric with respect to the y-axis. Is it symmetric with respect to the origin? In other words, both axes. Well, it would flip it here, and then would flip it here. Oh, there it is. Origin. We could try some other points, right? I'd do this one, I'd flip it, and then flip it, and there it is. Right? So this one is symmetric with respect to the origin. That is symmetric with respect to both axes there. And let's do this last final graph. Is this symmetric with respect to the x-axis? Let's take a point, flip it around. Hopefully you see, yes it is. So a circle is symmetric to the x-axis. Is it symmetric with respect to the y-axis? Well, take a point here, flip it over. Sure enough, it's symmetric with respect to the y-axis. So it also has y-axis symmetry. And then finally, does it have origin symmetry? Take a point, flip it, and flip it. Is it on the graph? Yes, it is. So it has origin symmetry as well. So now we're going to do this algebraically. We're going to test for symmetry. So I'm going to go back to these definitions. So if you're testing if something is symmetric with respect to the x-axis, what you do is you take the y and you replace it with negative y and see if you get the same thing. If it's symmetric with respect to the y-axis, you take the x and you replace it with negative x. You see if you get the same thing. And finally, to test if it's symmetric with respect to the origin, you take the x, replace it with negative x, you take the y, replace it with negative y, and if it simplifies to do the same thing, then you know you are symmetric with respect to the origin. Okay? So let's do some examples here. 4x plus y squared equals 4. So notice we don't have this graph. We're going to pretend we don't know what this thing looks like. Is it symmetric with respect to the x-axis? Well, here's an example of being symmetric with respect to the x-axis. I'm going to replace y with negative y and see if I get the same thing. That's how I'm going to test this. I'm going to replace my y with negative y and see if I get the same thing. Well, negative y times negative y is just a positive y squared. Is that what we started with originally? Hopefully you're shaking your head. Yeah, you're saying, yeah, that's what we started with. So yes, check. So yes, symmetric with respect to the x-axis. So again, we don't know what the graph looks like, but we do know it's symmetric with respect to the x-axis. Second question, what about, is it symmetric with respect to the y-axis? Well, if it's symmetric with respect to the y-axis, then we want to replace x with negative x and see if it gives us the same thing. So here's our original equation, 4x plus y squared equals 4. I replace x with negative x. And I simplify it. And I look at it. And I say, is that what I started with? No, I started with 4x plus y squared equals 4. I ended up with negative 4x plus y squared. This is not the same. No, not what I started with, right? So it is not symmetric with respect to the y-axis. It's not the original equation we started with. Is it symmetric with respect to the origin? Well, if it's symmetric with respect to the origin, this is an example that's symmetric with respect to the origin. Every xy will give me negative x, negative y. So I'm going to replace x with negative x, y with negative y, and see if I end up with the same thing. So 4x plus y squared equals 4. I'm replacing x with negative x and y with negative y, simplify it, and see if I get the same thing that I started with. Now, negative y times negative y is a y squared. Okay, I simplified it. Is that what I started with? No, I did not get 4x plus y squared equals 4. I got a negative 4x plus y squared equals 4. No. So the only thing this is symmetric to is the x-axis. That's the only symmetry that this one has. Let's go ahead and try this one. You can make that next one kind of a you try it problem. Great time to pause the video, work ahead to check your answers. So if we're testing this as symmetric with respect to the x-axis, that's that top one right there. We're going to replace y with negative y. So here's our original. We're going to replace that y with negative y. And that's as far as we go. Is that the same thing that we started with? No, it's not, right? We got something else. Now you could take the negative over to the other side. It would change both sides. On the other side, it's still going to be different, right? It's not what we started with. How about, does it have y-axis symmetry? Well, now we're going to take, this is the second one, right? We're going to replace x with negative x. X with negative x. So I got negative x there, negative x there. I replace x with negative x and see if I get the same thing. Well, negative x times negative x, x squared, negative 5 times negative 1x is a positive 5x. Is that what I started with? And not quite, right? We started with y equals x squared minus 5x. We ended up with y equals x squared plus 5x. So no. No symmetry again. So not symmetric with respect to the x-axis, not symmetric with respect to the y-axis. Is this thing symmetric with respect to the origin? Well, when we do the origin one, we're replacing x with negative x and y with negative y. Let's replace y with negative y, x with negative x. And let's see what we get. Negative y equals x squared plus 5x. Even if we take that negative to the other side, right, I changed all these signs. See how I'm still different than I started with? All right, I started with y equals x squared minus 5x, but I end up with negative x squared minus 5. I'm close, but I'm still not there. So there's no symmetry on this one at all. All right, there's your solutions for this one. And if you're checking it symmetric with respect to the x-axis, you replace y with negative y. Clean it up, not the same as what you started with. Is it symmetric with respect to the y-axis? Replace x with negative x, clean it up. It's not the same as what you started with. Finally, is it symmetric with respect to the origin? Replace x with negative x, y with negative y. And that one does clean up, if you notice, to be the exact thing that you started with. So this one is symmetric with respect to the origin only on this one. All right, so even and odd functions, this symmetry is a nice lead into even functions have this property. F of negative x equals f of x. So anytime you see a function that is symmetric with respect to the y-axis, it's going to be an even function. Because when you plug negative x in, it spits out the same y. F of x is the same y as when you plug in negative x. They spit out the same y. They have the same y value, x and negative x2. Right? So that's how you can test if you have an even function. So an even function, again, is another way of saying you're symmetric with respect to the y-axis. An odd function has the property, when I plug in negative x, it spits out negative, the opposite of f of x. It spits out the opposite of y. So I like to think about that cubic function that I drew that has x, y, and negative x, negative y. That's symmetric with respect to the origin. Okay, so an odd function is symmetric with respect to the origin. So let's test these. Are they even, odd, or neither? Well, let's test if this is even. If it's even, when I plug in negative x, it's going to spit out the original. So let's test that. F of x is x to the fourth plus 7. Let's throw in negative x. So it's just like when we're testing for y-axis symmetry. So the negative x goes in for x. Negative x to the fourth. Well, negative 1 to the fourth is positive 1x to the fourth, right? Is that what we started with? Yeah. So f of negative x is the actual original f of x, which was x to the fourth plus 7. So yes, that's an even function. If it was odd, when I plugged in negative x, it would have had to spit out opposite the original function. It would have had to spit out opposite the x to the fourth plus 7. That's how I would have known it was odd. Okay, but when I plugged in negative x, it spit out my original, so it's even. It's even. Okay. Let's look at this next one. Let's see if it's. Let's see. My next one is it even? Does f of negative x give me f of x? That's what we're trying to figure out. I got 6x to the fifth minus x to the third. Well, when I plug in negative x for x, I get negative x to the fifth is negative 1x to the fifth. Negative 1 times 6, so negative 6x to the fifth. Negative x to the third is negative x to the third. Negative times the negative in front is positive x to the third. Okay, is that what I started with? No, we started with 6x to the fifth minus x to the third, right? So it's not even. No, f of negative x does not equal the original f of x, right? That's not the original that we popped out. Well, is it odd? Well, odd says when I plug in negative x, it's got to give me the opposite of the original. Well, we plugged in negative x, and we got negative 6x to the fifth plus x to the third. So let's go ahead and take a negative out of those. And is this negative, is this the original that we had? 6x to the fifth minus x to the third. And hopefully you say, yeah, that's what I started with. That was my f of x. I did get negative f of x. When I plugged in negative x, I did not get the original. I got opposite the original. So this is odd. So the second one is odd. First one was even. Second one is odd. Right? So when I'm plugging in, when I'm testing for even, odd, or neither, I'm plugging it in. I see if I get the original. If I get the original, it's even. If I get a negative in front of the original, it's odd. If I don't get either one, it's neither. That's my even, odd, or neither. So let's go ahead and test this next one. I plug it in for negative x for x. I simplify it. Okay, that's not my original. F of negative x is not f of x, so this is not even. Now the question is, so not even. When I plugged it in, let's take a negative out of this. If I factor a negative out, is it opposite? Is this the original right here? No, my original was x squared plus x. I got negative x squared plus x when I took a negative out. So this is not, it is, when I plugged in negative x, I did not get negative f of x either. So this one's neither. This one's neither. C is neither. All right, let's test this next one. We've got f of x equals the absolute value of 2x all over x. If I plug in negative x, so I get 2 times negative x over negative x. So f of negative x is the absolute value of negative 2x over negative x. which the absolute value of a times b, you can split that up into absolute value of a times absolute value of b. So this is actually the absolute value of 2 times the absolute value of x. If you want to think about it that way, which is the absolute value of 2x, or 2 absolute value of x over negative x, which you can throw those back if you'd like. And then I'm going to take that negative on the bottom up top. Okay, is that the original? No, that's not what I started with, right? That is not the absolute value of 2x over x. It's negative 2x over x. So actually it ended up giving us, when I plugged in negative x, it gave me negative, that's the original. It gave me negative f of x. When I plugged in negative x, it gave me negative f of x. So this is odd. It's not even because it did not, f of negative x did not give me f of x. F of negative x gave me negative f of x. So it's odd. Okay? So that function's odd. Let's go ahead and test this last one. F of negative x, I get negative x cubed over negative x squared minus 9. So I got negative x cubed, negative x times negative x squared minus 9. Is that the original function? No. But it is opposite f of x. It is opposite the original. Remember, the original is x squared over x squared minus 9. So there is a negative in front of that. So f of negative x is negative f of x here. It's also odd. That one is odd as well. All right, so let's take a look here at piecewise defined functions. Here's the function defined over here. Use this function right here to find f of negative 4. Okay, f of negative 4. So I'm trying to decide, if I'm plugging negative 4 in for x, is negative 4 less than negative 3, or is negative 4 greater than or equal to negative 3? Well, hopefully you know that negative 4 is less than negative 3, so you're going to use the top one. Right? So f of x, you're going to use the top one because negative 4 is less than negative 3. So you plug that negative 4 in, and you get negative 2. So f of negative 4 equals negative 2. Now let's do the next one, f of negative 3. So then I'm asking, is negative 3 less than negative 3, or is negative 3 greater than or equal to negative 3? And hopefully you know that it is or equal to. So you're using the bottom one. F of negative 3, since negative 3 is greater than or equal to negative 3, you're going to use the bottom one. So f of negative 3 ends up being negative 5. Next one is asking us, how about f of negative 3 halves? Well, negative 1.5, is negative 1.5 less than negative 3, or is negative 1.5 greater than or equal to negative 3? And hopefully you recognize that it is greater than or equal to negative 3. So you're going to use that bottom one, f of x equals x minus 2. So f of negative 3 halves is negative 3 halves minus 2. So we got negative 7 halves. F of negative 3 halves ends up being negative 7 halves. All right. And then if you're graphing this, what I like to do when I graph these is I'll take the first one, f of x is x plus 2, and I'll make a table of values. And notice this is for any values less than negative 3. So I'm going to start at negative 3, but I'm going to make it open because it's less than. And I'm going to pick values that are less than negative 3, and I'm going to plug them in one by one and plot the points. So I plug in the negative 3. So negative 3 plus 2 is negative 1. Then I throw in negative 4 plus 2. And negative 5 plus 2. I plug them in one by one, negative 6 plus 2, and so on. And I'm going to graph them. Negative 3, negative 1. Now that's an open hole. Negative 4, negative 2, I'm going to close that. Negative 5, negative 3, I'm going to close that. Negative 6, negative 4. So it's all these values that are less than negative 3. Right? So I'm going to connect the dots. We're graphing the line y equals x plus 2, but only where it is less than negative 3. And then I'm going to go to the next one. Y, or f of x, equals x minus 2, but it's only for when it's greater than or equal to negative 3. So I'm going to start at that negative 3, greater than or equal to, but this one's going to be closed because I'm including negative 3 this time. And I'm picking values greater than negative 3. Greater than negative 3. As many as I think I need to draw this line. I'm going to plug in the negative 3 minus 2. I get negative 5. I'm going to plug in the negative 2 minus 2, which is negative 4. Negative 1 minus 2. 0 minus 2. 1 minus 2. And 2 minus 2. So negative 3 comma negative 5. I'm going to plot that. I'm going to fill it in, right? Negative 3, negative 5, there it is. Negative 2, negative 4. Negative 1, negative 3, 0, negative 2, and so on. I can draw as many as I need, but it's only those values where I am greater than or equal to negative 3. And there's my piecewise defined graph for that. So here we got a new piecewise defined function. We got f of negative 1. So I got to decide, is negative 1 less than 1 or is negative 1 greater than or equal to 1? Hopefully you know negative 1 is less than 1, so I'm using I'm using the top one, negative 1 half x squared, when I plug in negative 1. And we know negative 1 squared is positive 1, so negative a half times 1, negative a half. F of 1, is f of 1 less than 1 or greater than or equal to 1? Well, hopefully you know that that is greater than or equal to 1, so we're using that bottom one when we plug 1 in. So we got 2 plus 1, we got 3. So f of 1 is 3. F of the square root of 9/10. Well, I got to decide, is the square root of 9/10, is that less than 1 or is it greater than or equal to 1? Well, square root of 10/10 would be square root of 1, which is 1, right? Well, this is square root of 9/10, so I'm going to be less than 1 on this. So I'm going to use that top one. Square root of 9/10, so that's kind of bad. Square root of 9/10, and it's squared. So when I square that, that'll undo the radical there, so I end up with negative 9 over 20 when I plug in the square root of 9/10 on that. All right. Now, when we're doing the graphs for this, let's go ahead and do that first one. F of x is negative a half x squared, and x is less than 1. So this is a quadratic. So you're thinking U-shape. The negative in front is going to flip that over. So your typical U-shape x squared looks like that. It's going to flip it over. That's what it's going to kind of look like. But I can only plug in points that are less than 1. So 1, 0. Now 1 is not included, so I'm going to leave that open. So I can only plug in a handful of points that are less than 1. So let's plug in 1 and negative a half times 1 squared. Well, 1 squared is 1, so f of 1 ends up being negative a half. But remember, that's open. So negative 1, or I'm sorry, positive 1 down a half. So right there, but it's open. Plug 0 in, so f of 0. So I got negative a half times 0 squared. Well, 0 times anything is 0. So f of 0 is 0. Plug in negative 1. So f of negative 1 is negative a half times negative 1 squared. Well, negative 1 squared is positive 1. So we end up with negative a half on this. So negative 1, negative a half. Plug in negative 2. Well, negative 2 squared is 4. So I got negative 4 over 2 is negative 2. Plug in negative 3. Negative 3 squared is 9. So I got negative 9 halves on that one. So negative 4.5. So about right there. Anyways, I could keep going with this, but you kind of got an idea. That's that part of that piecewise defined function. It's that flipped over quadratic whenever x is less than 1. So now I'm going to erase all this, and I'm going to do it for my other part of this. Let's do this in black. F of x equals 2x plus 1. So I got the line whenever x is greater than or equal to 1. So I can include 1 this time. So I'm going to close it, or make it a filled in hole there, but pick values bigger than 1. So let's plug in 1. F of 1 would be 2 times 1 plus 1. 2 plus 1, 3. Plug in 2. 2 times 4 plus 1, 5. 2 times 3, 6, plus 1, 7. 2 times 4, 8, plus 1, 9. So I got 1 comma 3. It's filled in, so make sure that that's closed. 2 comma 5. 3 comma 7, and so on. And this is a straight line. So the line y equals 2x plus 1, but only where x is greater than or equal to 1. One more function notation example before we graph it. I got f of 0, so I'm trying to decide which of the three it is. Well, 0 is greater than or equal to 0, so I want to plug it into that bottom one, x squared minus 1. So I got 0 squared minus 1. 0 minus 1 is negative 1. F of negative 1, well, negative 1 is less than 0, greater than negative 3, so I'm using the f of x equals negative x on this. So f of negative 1 is negative 1. So f of negative 1 is positive 1. Will be that one. F of square root of 10 over 2. Well, square root of 10 is between square root of 9, which is 3, and square root of 16, which is 4. So it's like 3 point something over 2. So if you plug this in, you get 1.58. Maybe that's how you want to think about that. That's 1.58. So I'm greater than or equal to 0. So I want to use that bottom one, x squared minus 1. So square root of 10 times square root of 10 is just 10. 2 squared is 4. So I get 10 fourths minus 1. So I get 5 halves minus 1. 5 halves minus 2 halves, or 3 halves. Negative square root of 11. Well, square root of 11, that's between square root of 9 and square root of 16. So this is negative 3 point something. In fact, if you plugged it in, it'd be negative 3.32, I believe. So you want to go back up here. You say, well, negative 3.32, that's less than negative 3. So I want to use that one, f of x equals 0. Whenever x is less than negative 3, it is. So f of negative root 11, there's nowhere to plug it in. It's just automatically 0 on that one. So now when we're graphing these, let's do this f of x equals 0 first. Let's do the graph y equals 0 whenever x is less than negative 3. So less than negative 3. So I'm open, but anytime I pick values less than negative 3, it's always 0. It's always 0. So negative 3, 0 is open. Negative 4, 0 is closed. Negative 5, 0, and so on. So it's all these. That's that line y equals 0, but only where x is less than negative 3. Now for the next one, let me do this one in red. F of x, y equals negative x, where I'm between negative 3, including it, and less than 0. So I'm less than 0, so that's open, less than 0, but greater than or equal to negative 3. So negative 3 is included. That one's going to be closed. And I'm going to plug it in to this negative x. So f of 0 is negative 0. Well, that's just 0. F of negative 1 is negative 1, so that'd be 1. F of negative 2 would be negative 2. F of negative 3 would be negative 3, which is 3. So 0, 0 is open. Negative 1, 1 is closed. Negative 2, 2 is closed. Negative 3, 3 is closed. So it's between here, oops, and there. I'm going to draw that line. So there's that line, negative x, but only from negative 3 up until 0, not including 0. The last one here, we have f of x equals x squared minus 1 for values greater than or equal to 0. So I'm closing, it's including the 0, and I'm picking values greater than or equal to. So I'm going to plug in the 0 first. Then I'm going to plug the 1 in next. Then I'm going to plug the 2 in next. And finally the 3 in. 3 squared, 9 minus 1 is 8. So we have 0, negative 1, that is closed. 1, comma 0, 2, comma 3, 3, comma 8, and it's a quadratic x squared, so it's got a little curvature to it, but it's going to keep going. And there's our pretty decent graph for that piecewise defined function. Well, the difference quotient, this is actually a conversation that you use quite a bit in calculus, and what it's used for is to find the slope of a secant line. So if I call this point x and I go out a distance of h, so this is x plus h, and let me put the points on here. I have x, f of x, and I have this point x plus h, f of x plus h. Well, if I want to find the slope of the secant line that goes through those, right? So my secant line. Then I would use that slope formula. Remember the old slope formula is y2 minus y1 over x2 minus x1. Well, the y2 here is that f of x plus h minus, that's the y2. Oops. Right there. There's my y1 minus f of x. All over x2. Here's my x2 and here's my x1. And notice my x's cancel. So this is the slope of the secant line. Slope of the secant line, which we refer to as the difference quotient. Because this difference quotient, when you get into calculus, is going to be used to find the slope of the tangent line. So you're going to work with this quite a bit when you get into calculus. Again, this is called difference quotient. And eventually what it'll do is it'll help you to find the slope of the tangent right there. That's what we're going to want to find in calculus, is that slope of the tangent right there at that point. Okay, but we're going to use this difference quotient. Again, discussion for another time, but that's a little bit of introduction to the difference quotient. So the difference quotient is f of x plus h, y2 minus y1 over x2 minus x1. But again, the x's cancel, so you just have the h on the bottom. So let's go ahead and find the difference quotient for this one. Here we have f of x is 2x minus 3. Well, notice in the difference quotient, I need f of x plus h. So I got to throw in x plus h anywhere I see an x. There's my f of x plus h. So this difference quotient ends up being, let's go ahead and fill this out. Here's my difference quotient. F of x plus h is 2x plus h minus 3. There's my f of x plus h minus the original function. Well, what's the original f of x? It's 2x minus 3. Now there's two terms there, so make sure you put that in parentheses. So again, this is my f of x plus h minus, there's my f of x. And this is all over h. And now we're just going to simplify this. So we got 2x plus 2h minus 3 minus 2x plus 3 all over h. And the idea is you're trying to get that h to cancel on the bottom, but let's go ahead and simplify this. Notice I have 2x minus 2x, that's going to be gone. I have minus 3 plus 3, that's going to be gone. So I'm just left with 2h over h, and my h's are gone. So my difference quotient just ends up being 2 here. Just ends up being 2. And that's actually telling you the slope of the tangent line for this function, by the way. Find the difference quotient for this one. So again, we're going to find the difference quotient. So we're going to have f of x plus h minus f of x, y2 minus y1 over x2 minus x1, but remember the x's cancel. So we just have an h on the bottom. So let's split this. Remember, so let's look for f of x plus h. Well, f of x is 3x squared minus x plus 1. So f of x plus h would be 3 x plus h squared minus x plus h minus 1. That's our f of x plus h. So let's put that in right there. F of x plus h is 3 x plus h squared minus x plus h plus 1 minus the original f of x. Well, the original f of x is 3x squared minus x plus 1. And then this is all over h. And we're going to distribute that. We're going to expand this x plus h times another x plus h. We're going to distribute that. It's all over h. Now I've got to FOIL this. So I have x squared plus xh plus an hx, which is xh, same thing, plus h squared. Minus x minus h plus 1 minus 3x squared plus x minus 1 all over h. Now notice I have xh plus hx, so that's 2 xh's. I'm going to distribute. X squared minus 3x squared. Notice that is gone. I've got a minus x plus x. That's gone. I've got a plus 1. I got a minus 1. That's gone. So it looks like I have 6xh plus 3h squared minus h. This is all over h. Now remember, we're trying to get the h's to cancel. So I should be able to take out an h out of each of these terms, which I can. Factor an h out, and then see how those h's will cancel. That's nice. And so I end up with 6x plus 3h minus 1. And there is my answer to my difference quotient. Well, thanks so much for taking notes and finding difference quotient and all this other stuff. I'll see you next time.